Welcome to the Scopes screencast. Today I'm going to talk about loops and constants. The last time we wrote a very simple loop in form of a recursion, which is not the most elegant way to do this, but the most primitive way if you only have functions. I always like to explain everything starting from functions, because with functions you can do everything. There's there are very nice principles based on this. If you Google for church encoding, you can find a lot of interesting explanations about how you can use functions to do nearly everything. And internally, the language does a lot with functions to a certain degree. So let's start with the loop recursion we had from last time with the little modifications. We are going to write a screenplay generator for a Simpsons episode where Homer Simpson only says dough. For that I'm going to write a function that is named Homer says dough. And it takes one argument, which is the number of times that Homer is going to say it. We're going to print the screenplay output for that. And then we are going to repeat the function by calling it again with n one level smaller. And also we have to make sure that the function is actually not running forever. So we check if n is bigger than 0, and if yes, only then are we going to execute the function. So we're going to generate a screenplay where Homer says dough 10 times. And there we go. So what if we wanted, for clarity's sake or for elegance, or we want to write the line number of, let's say we want to print the line number of the screenplay as we write it. And if we just print n in front of it, then we are going to get a counter that starts from 10 and counts backwards, which is not how line numbers in screenplays work. We need a forward counting counter, and we're going to start with, we initialize a counter extra for that. We are going to keep n alone. And we're going to say if I is smaller than n, then we are going to print it, otherwise we do nothing. And that causes the function to return. And we're going to pass a bigger I each time. And we start with 1. And we say that it's smaller or equal because we started with 1. And if we execute it then, we are not getting the right result because I'm still printing the wrong value. But now that I'm printing I, it's working correctly, and we are going to see line numbers. So what sucks a little is that the user has to pass a counter init value from the outside, which is 1 assigned to I here. And we want to keep this counter internal, so the user only has to care about passing how many times he wants Homer to say dough, and not care about how it works internally. So we are going to initialize a variable to 1 with the mechanism you have seen in the last video. And now we are going to, the problem is how do we do this? We can either write a function within a function and then call that function, or we can use something a little bit more elegant, which is basically shorthand for what we just did, which is to use a named-let. A named-let works by first putting all the values you want to initialize in the parentheses, like the same way you define parameters in a function. That's actually how it works. And then you give the let a name, like for example loop. You could also call it repeat, or again, but we are going to call it loop. So what else do we have to change? We are not calling the main function anymore. We are going to call the loop. We only need to pass I because n is outside the loop. And basically we're calling loop with the same arguments that we defined here and initialized here. So this part is only executed once. One is assigned to I when we first enter the function. Then the function, the value is checked against our maximum. And if we are still running, then we are going to execute the body of the function. And then we call the loop with I incremented by 1. And at this point, I is then 2. We check 2 against n, and so on until I is 10. And then until I is 11 actually, and then this part will not run anymore and we are exiting the function. So let's see if that works. Yep, it does. And that's how a named let works. So the named lets are, I like to use them a lot because they're so useful. But if you want to have more traditional loops, with mutated variables, then that is possible too. Like if you are, for example, coming from Python or from C, you might be more used to something like this. You initialize I to 1. And then you say for I in, and we are going to pass a range generator here. Basically, what for is just a macro that basically does internally very much the same stuff we've seen before with a few more bells and whistles using a named let. But from a user standpoint, we are going to talk about macros in a later talk. From a user standpoint, this is not particularly important how it's implemented as long as it works. And range is a function that returns a generator which counts from from 0 to n. And if you pass it 2 numbers, which we would have to do here, then it starts here with this number. Oh well, let's just try it out. So by default, we are always counting from 0, and we are starting 1 number less than n, which is basically how C or Python coders expect it. But that means, of course, that our line number is wrong. We can either fix it here by incrementing I each time, which fixes the result, or we can change the range indicator by not starting from 0, but from 1, and then count to n plus 1, and that is doing the same. That has the same effect. So that's how for works. And then there's also while, of course. And in this case, we don't run an automatic counter. So we have to use a mutable variable for that. Mutable variables are not declared with let. Like if I assign 0 to I here, then I can't change I again. This would be an error. If I want to be able to change I again, I have to use var for a variable, which declares then I as a stack variable, which has a little bit of memory allocated and is internally of reference type. And then I can change I to something else. And then we are going to write a while loop, which says as long as I is smaller than n, we are going to print it. But we have to take care that I is actually being incremented, which is done like this. And there you can already see that I is by default of a different type, and the printer prints all the default types without a type annotation, because you know what those are. But if the type is a little bit different, then you are seeing these yellow annotations like this one, which shows you exactly what type this value is. So if you want to get rid of that for beautification, you can cast I to immutable, and then you are getting the same result as before. And that's while for you, which you probably don't need much, but if you insist you gotta have it, then it's there. I mostly use named lets because they are so elegant. They don't need mutable variables, and they are very efficient to translate into assembly. So those are my favorites. So let's talk a bit about loop unrolling. We're going to do another simple named let loop, which is, or just go back in the history to the point where we had it. Yup. So what happens if I pass something big here, like 100 times? Something weird happens. I'm going to get an error, which is maximum number of recursions exceeded during compile time evaluation. And then a number that is probably the maximum number of recursions, which is 32. I currently set it to 32. I want to make it configurable, but this is basically, trap, because this is basically a convenience trap, because the idea here is that if we have a constant expression, that is, we can completely compute the expression during compilation, and there are no parts in the expression that that depend on something that the user has to input, or some system values, or some stuff that we only know at runtime, then the compiler guarantees that it completely computes the entire expression for you at compile time. So what happens in reality with this loop is that it's being unrolled before the program is even compiled into about 100, or before it was 10 print statements with the right number put in here, because everything here can be evaluated before the program is even running, because there are no surprises here, there's no user input, so everything can be folded. And if we have an infinite loop, then the problem is that it would practically fold forever. There's no way to detect these infinite loops in every case, because of a problem in computer science called the halting problem, which basically states that it's impossible to detect how long, to calculate how long a program will run and if it will ever terminate. And because we can't do that here either, during loop unrolling, we are going to say, okay, we assume that after 32 loops, this is probably not your intention, and it was supposed to be generated into the final program. Basically, if we do so many loops, we don't want to generate a print statement for every loop, but we want to just generate the loop itself and run it and evaluate and compute a little, because that makes for a much smaller program. So how do I get it to actually run 100 times? So the very simplest way to do that is, if one here were not a constant but were a variable, then the loop would definitely not be unrolled logically, because then the check here would no longer be constant, would not always be computable, and that means we have to keep the whole loop. So the easiest way to do that is to use a special internal function called unconst, which turns the constant into, basically pretends that the value here is not a constant but a variable, and then the whole thing is caused to be no longer constant either, and then the unrolling doesn't happen, and then the program is executed. So now it runs, and basically the assembly that is generated in the background looks much different now. But we're going to talk about debugging, disassembling on the fly and so on in a later talk, actually in the next talk. And suffice it to say that this time loop unrolling is something you have to look out for, and you have to occasionally unconst the variable if you want to support both modes. That is, the loop is unrolling if it's trivial, and it's not unrolling when it's complex, which is completely up to you. So another problem to look out for is when you have a loop written out as a constant, but the termination variable isn't constant. Like if n, for example, is something that is determined at runtime, that is, we don't know how many times the loop will run, we are also getting this problem. So you would say the easiest solution to that is just have always a non-constant loop, which would indeed fix the problem. But what if you want to write a loop that unfolds when the input argument, you see, if the input argument, for example, is something smaller than 32, you want to definitely unroll it and otherwise not unroll it. And how do you support both modes when you have a counter that is never constant? So you need some way to tie the constantness of the counter to the loop count argument. And there's a tool function that does this, which is called tieConst, which says tie the constantness status of the first argument to the second. Basically, you can also check if n is constant with the constant internal function constant, which gives true if n is constant and false if it's not. So we are now going to tie n, the constantness of n, to our initializer. And in this case, we can see here that n was constant. So we know that the loop has been unrolled. In this case, we would now get an error because n is still constant. So the user outside would have now to take care to unconst such a huge value. And if it's not const, we're going to see in the beginning that's reported to be false, as expected. And then the correct constantness is tied to the initializer, and then the loop works correctly. So this looks a little bit complex because in other languages you don't have this problem, but you have other problems. For example, in C and C++, there's no way to control how unrolling and when unrolling works exactly. This is an internal heuristic to the compiler, and if you'd like to have more control over when and how it happens, there's basically no way from the language to control this. So you can't exactly ever dictate which expressions you want put into the final program, which expressions you want to have evaluated at compile time. And there's also no way to check if a variable that comes in is actually known at compile time or not. So we have these neat little tools to have more control over what we are producing. And basically they fell out during language design as a solution, and I liked it so much that I thought it's worth keeping it, and I hope they will be useful to many of you. So this concludes the talk. That's actually everything we need to know for loops and constants right now. In a future talk, I'm also going to talk about generators and how to write them, which is a bit more complex topic. And that's it for today. Thanks for watching.